Alright, hi everyone, welcome back. In today's video, we want to cover the principle of continuity in multivariable calculus. So what this means is that we are going to take what we learned about limits and what we know about continuity from single variable calculus, and we're going to use it to describe multivariable calculus and multivariable functions and how they are continuous and how we can describe them as such. So one of the first things that we want to do is we want to expand upon the idea of continuity in the single variable case. So the definition of continuity for the multivariable case says that a function is continuous at an ordered pair a comma b if the limit as xy approaches ab of f of xy equals f of ab. So that means that the function is defined at the ordered pair. So if the function is defined at the ordered pair, then that means that the function is continuous at the ordered pair. Okay, so how do we expand on this? So the function is continuous on a set domain if the function is continuous at every point in the domain. So if we have tons of a comma b's covering a whole domain and it's continuous at each one of those, then the function is continuous on the whole domain. All right, so let's try a couple of examples, and then I want to finish off with just an idea of multivariable limits as a whole as we wrap up our study of limits. So I would like us to determine the value of the limit as xy approaches 3, 4 of x squared y cubed plus x squared y. Now, I said that it's really hard to determine the values of a lot of limits just because of, well, how much time it takes to do an epsilon delta proof. So what we're going to do instead is we are going to recognize the continuity of this function, right? So x squared y cubed plus x squared y, this is known as a multivariable polynomial function, right? Because a multivariable monomial is a multivariable monomial is x to the m times y to the n, and that's a two-variable monomial. So two-variable polynomial is the sum of a bunch of two-variable monomials. So what we have here is a two-variable polynomial, and what we know about polynomials in single-variable calculus is that they're always continuous. And that's the same for multivariable polynomials, they're always continuous. So in fact, instead of doing an epsilon delta proof, it will suffice, as long as we can prove that this is continuous, we say, since f of xy is a continuous function because it is a polynomial, we can do a direct substitution into this limit to determine what its value is. So p of xy is continuous for all x and y. Thus, the limit as xy approaches 3, 4 of x squared y cubed plus x squared y is just equal to the direct substitution. So 9 times 64 plus 9 times 4. Pull out your calculator, folks. So this is a one I don't want to do tons of mental math on, but the answer that we get is 612. We can see this on the graph. This graph is continuous everywhere, right? We're continuous across both of our axes. We don't really have any issues here. It's just a very steep trace here of this parabola there and this parabola there. But these are just second order and third order terms. So it's nothing too crazy. So we've determined the value of the limit, and that's really basically a fancy way of saying we've determined the value of the function there. Anyways, let's try another one. Where is f of xy equals x squared minus y squared over x squared plus y squared discontinuous? Okay, so where would this be discontinuous? Well, we think it would be discontinuous at 0, 0 because the denominator would be 0, right? We've got x squared plus y squared. The only thing that messes up our continuity is when the denominator of a rational function is equal to 0. And because these are both positive, because they're squared, the only time is when x and y is 0. That's the only time when the denominator would be 0. So thus we're discontinuous at 0, 0 because the denominator is 0. We can take a look at this on the graph. I think we may have done a problem with this graph before, but anyways, here you can see we've got a big hole here. This guy, as we trace along this axis here, we are trying to get about to 1 there for height. But as we trace along this one here, we're trying to get to -1, it looks like. That's not good. So what we have is we have a discontinuity there. That should make sense. Now, finally, I'd like to finish our study of limits. We talked about limits of two-dimensional functions. Now I'd like to bring it up to n-dimensional functions. So let's say D is a subset of R sub n, and X is an n-dimensional vector. So I'm going to use vectors and coordinates interchangeably, right? Because if I have a point A, B, C, I can also represent that by a position vector A, B, C, right? So basically, if I say X is an n-dimensional vector, X is really just an n-dimensional point. So given that X is an n-dimensional point in D as a subset of Rn, then the limit as x vector approaches a vector of f of x vector equals L. So f of x here, this is equal to a function of n different variables. So x1 all the way to x sub n. So this is a function of many different variables, an n-dimensional function. So if that's L, then that means for every epsilon greater than 0, there's delta greater than 0. And then for delta greater than 0, instead of doing x minus a squared plus y minus b squared, we do something else. So we take